we know that permanent magnets, like bar magnets, create magnetic fields. And they're also affected by magnetic fields. This sort of duality, this interaction, this behavior is not kind of unique to magnetism. We saw this with gravity as well. Mass, an object with mass, creates a gravitational field. It's also affected by other gravitational fields. An object with charge creates an electric field. It's also affected by other electric fields. And now we see this is true for magnets as well. In fact, that is how magnets push and pull on each other. One magnet creates a magnetic field around it, and the other magnet is affected by that. Either it's pulled or it's pushed by that magnetic field, and vice versa. Now, the same is true for moving electric charges. What we've seen just recently is that a moving electric charge, like current running through a wire, has a lot of the same properties as a permanent magnet. Both of them create magnetic fields. So moving electric charges also create and are affected by magnetic fields. Now, to help us sort of visualize and understand how this creation of magnetic fields and affected by magnetic fields works, we've got a couple of mnemonics. The way a moving charge creates a magnetic field, we studied that already, and that was described by the first right-hand rule. So it turns out the way a moving charge is affected by a magnetic field, that is described by what we're going to learn shortly, and it's called the second right-hand rule. So we've got one right-hand rule that tells us how a moving charge creates a magnetic field, and another right-hand rule that tells us how a moving charge will be affected by a magnetic field. So, as we kind of have been using previously, the simplest example of a moving electric charge is current flowing through a wire. So let's look at that. Let's look how current flowing through a wire is affected by a magnetic field. And we're going to sort of demonstrate the second right-hand rule in that context. So, let's say we have current flowing through a wire being affected by a magnetic field. We want to analyze this situation using the second right-hand rule, which I'm about to show you. So, step one is use your right hand. That's pretty key for the right-hand rule. Step two is to aim your thumb in the direction the current is going. So we've got a wire, it's carrying electric current. We take our thumb over here and we point that in the direction that the current is flowing in the wire. Step three is you then take your pointer finger and you kind of put your thumb and your pointer finger at 90 degrees to each other like this, kind of to make like a little gun symbol. And your pointer finger goes in the direction of the pre-existing magnetic field. Now, the reason I say pre-existing is because electric current will create its own magnetic field, but that's not the magnetic field that we're looking at over here. The magnetic field that we're looking at over there already existed before we had that current. That's why I say it's a pre-existing magnetic field. So, I have a magnetic field that already exists, and then I have some current, electric current, running through that field, perpendicular to it. Step 4 says aim your middle finger so it's coming out of your palm, perpendicular to both of the other directions. So I should have a 90-degree angle between here and here. And I should have a 90-degree angle between here and here. And as we already discussed, I have a 90-degree angle between here and here. So your thumb, your pointer finger, and your middle finger are all at 90 degrees to each other, with your middle finger kind of sticking straight out from your palm, almost out of the screen in this example here. So what your middle finger tells you here is the direction of the force exerted on this current by this field. That's the essence of the right-hand rule. Let's run through that one more time. When I have an already existing field going in this direction, and then I run some electric current in a wire through the field in this direction, that current will feel a force in this direction. So that tells us about the direction of the force on a current carrying wire in a magnetic field. Let's now get a formula that'll tell us about the magnitude of that force. So this formula looks like this. F equals ILB, and there's a little perpendicular symbol in there. So let's label some stuff here. B is our pre-existing magnetic field. Right, before I have any current or any force, I've got this magnetic field. That's this guy up there, my pointer finger. Then I is the current that's then introduced. L, we've got a magnetic field, then I suddenly have a wire with current running through it. L is the length of that wire, specifically the length that's in the magnetic field. And finally, F is the force on the charge by the field or from the field. And that is basically what our middle finger over here was denoting. It's probably worth just really briefly throwing some units in here. So the magnetic field, as always, is going to be measured in Teslas. The current, as always, is going to be measured in amps. Length of wire, that's going to be in meters. And force, that's going to be in newtons. Now, let's talk about this little symbol here. It's not the first time we've seen this symbol. We've seen this symbol before in our torque formula. We've seen a similar one in our work formula too. This symbol means that the wire and the magnetic field need to be perpendicular to each other. Kind of like how we said over here, the current and the field need to be perpendicular to each other when I'm using my right hand. So what happens if they're not perpendicular? Well, if they're perpendicular, then this formula works great and there will be a force. If they're not perpendicular, well, it depends how not perpendicular they are. If they're parallel, I say, well, parallel is pretty much the opposite of perpendicular. So I'm going to get pretty much the opposite of a force. I'm going to get no force. So let's write some notes down about this. If the wire is perpendicular to the magnetic field, then great. This condition here has been met, and we can just plug numbers in. If the wire, however, is parallel to the magnetic field, well, like we said, parallel is kind of the opposite of perpendicular, so we're going to get the opposite of a force. We're going to get no force. F is going to be 0. And you might be kind of thinking, well, that leaves a lot of other possibilities. Perpendicular and parallel are just two angles. There's a whole bunch more angles. And if we're looking at one of those situations, what we're going to do is we're going to take that magnetic field or that length of wire, and we're going to break them into components. One component where we do have it being perpendicular, and one component where it isn't. And then we can look at those components separately. We won't be doing a lot or probably any of that in this course, but I thought we'd mention it because that's something that we're familiar with. We did that with torque, and the same concept would apply here. Okay. So let's take what we've said here. Specifically, let's take that second right-hand rule. No formulas yet. And let's apply it to a scenario. Imagine a current-carrying wire placed between two permanent magnets, as shown below. Here's my current-carrying wire. So this wire is sort of running into and out of the page. We're looking at that circle we're looking at is just a cross-section of the wire, as if it's been sort of sliced down the middle. And here are my two permanent magnets. Which direction will the force be on the wire? Okay, so if we're going back to our second right-hand rule, which is the relevant rule when I have current in a magnetic field feeling a force. Let's recap what the key points are. I've got an already existing magnetic field. Finger goes in that direction. Then I put my thumb at 90 degrees to my finger, and I put my thumb in the direction of the current. Then I put my middle finger at 90 degrees to both of those, and it tells me the direction of the force. So if you take your right hand, it's hard for me to demonstrate this in the video. First thing we have to do is put our pointer finger in the direction of the magnetic field where the wire is. Well, let's figure that out. This wire is pretty close to the ends of a magnet, so there should be a strong magnetic field there. But which way does it go? Well, recall that magnetic field lines go from north to south. So there should be some magnetic field lines going in this direction here, where this wire is. And we will probably have some magnetic field lines that kind of come out here and go around to that south over there. There will be a little bit of that happening. But for most of these magnetic field lines, the closest south pole they can get to is this one over here. So that's where a lot of them will go to. Okay, so now we can take the pointer finger of your right hand and point it to the right, the direction these arrows are going in, the pre-existing magnetic field. Then, making that sort of gun shape with your hand, point your thumb in the direction of the current. Well, this is my current here. It's going into the page. Remember, an X means into the page. So pointer finger going to the right, thumb going into the page, and now stick your middle finger sort of at 90 degrees to both of those, sticking out of your palm, and you'll notice that your middle finger points down the page, towards the bottom of the screen or towards the bottom of the page. And that's the direction of the force. So this can lead to sort of odd behavior. If you had this wire sitting between these two magnets, hooked up to an electric circuit, and suddenly I hit a switch and current starts to flow, the wire would suddenly jump downwards. And it would be a little tricky to kind of figure out intuitively what suddenly caused the wire to jump downwards when current flowed. But now you know it would have been this force from that magnetic field. Now remember, a moving charge, like I have in this wire here, is not just affected by a magnetic field, but it'll also create its own magnetic field. And we didn't look at that magnetic field in this problem, but it becomes important in these next examples here. So in these examples, we see how both the creation and the being affected by the magnetic field can sometimes be important. Picture two parallel wires carrying current in the same direction. Would the wires attract or repel? So let's tackle this. It just said these wires are going to carry current in the same direction. Doesn't matter whether it's into or out of the page. Let's go with into the page. Just kind of pick that randomly. So this wire is carrying current into the page. And I'm going to use a different color for the other wire. This wire is carrying current into the page. So first of all, each of these wires is going to create a magnetic field in the way that we discussed in the last lesson, according to the first right-hand rule. Remember, the first right-hand rule is for the creating of the field, and the second right-hand rule is for the being affected by the field. So, first right-hand rule, I take my thumb of my right hand, I point it in the direction of this current, and I make a fist with my fingers, and I see that my fingers then are going clockwise around that wire. So I will have a magnetic field going clockwise around this wire. Now I'm not going to draw that magnetic field everywhere. I'm just going to draw what it looks like in the region of my second wire. So I kind of have a magnetic field that'll be going like this. There's my red magnetic field created by the red current in this wire. Now at the same time, my green wire is going to create its own magnetic field from its current. And I can use the right-hand rule for that too. So if I'm in the direction of that green X, so into the page, I see my fingers then are going clockwise, and this guy is going to create a clockwise magnetic field around it. And again, we won't draw the whole field. We'll just draw a few of the field lines over here where the other wire is, because that's the region we're sort of interested in. So each of these wires is creating a magnetic field where the other wire is. And now each of these wires is going to be affected by the other one's magnetic field. And for that affected part, we're going to use the second right-hand rule. So let's look at the front side here first. Here I have a already existing magnetic field. This magnetic field has nothing to do with this wire that I've highlighted. It's coming from the other one, and it's going up. So my pointer finger goes up. Then in that magnetic field, I have current flowing into the page. So while my pointer finger stays up, my thumb is going to go into the page. And then my middle finger, if I stick it out from my palm, perpendicular to both of those, I see that it is pointing to the right. So the force felt by this first wire from the second wire's magnetic field will be to the right. Should label all these. So these green arrows here, that's B, my magnetic field These guys are B magnetic field 2. Okay, now let's look at the second wire, the one on the right. It is in a magnetic field that's going down. So pointer finger goes down. It has current going into the page. So thumb goes into the page while pointer finger still goes down. Now I look at my middle finger, I see that it's pointing to the left. Just listening to me go through this probably isn't going to make a lot of sense. What you really want to do is actually do these actions with me as I'm saying them out loud. Get your right hand in front of you and try and reproduce this. So, this seems to tell us that when I have two parallel wires carrying current in the same direction, they will attract each other. Notice how each one feels a force towards the other one. Now, how about if I have two wires carrying current in opposite directions? Good guess might be that they're going to repel, since that's sort of the opposite behavior. But let's just double check. So I'm going to make this first wire have current going into the page, like we had last time. So it'll create a magnetic field like this. But I'm going to make this second wire have current coming out of the page. So that means the magnetic field it creates, and I can verify this using my first right-hand rule, is going to be counterclockwise around that wire. And I'm only going to draw the parts of that magnetic field that are over here where this wire is. Okay. So that's the part where both of the wires create their magnetic fields. Now we're going to look at how they're affected by the other magnetic fields. So take your right hand out. We'll look at the left side first. Here I have a magnetic field going down the page. The green arrows. So point your pointer finger in that direction. And I have current going into the page. So get your thumb in that direction. Now stick your middle finger out, perpendicular to both, and you see that it's going to be going to the left side of the page. So that's the force that'll be felt by this wire. And we do the same thing for the other wire. Finger goes down the page because that's the direction of the magnetic field. Thumb comes out of the page, and then we see our middle finger is going to be pointing to the right. So these wires are not attracting each other. They are, as we suspected, repelling. Now, these two examples have been really focused on understanding the concept here and getting the direction down. I think it's best if we do at least one example where we've got some calculation involved as well. So let's do that now. A wire carrying 3 amps of current to the right sits in a 0.5 Tesla magnetic field coming out of the page. I am going to draw this. So we've got a magnetic field coming out of the page. That means dots. So there's my magnetic field, 0.5 Teslas. And I've got a wire carrying 3 amps of current to the right. The wire is 1 meter long. So from here to here is 1 meter, but only 30 centimeters of it are in the magnetic field. So from here to here is 0.3 meters. What is the direction and magnitude of the force on the wire from the magnetic field? Well, let's do the magnitude part, because that's the one we haven't really practiced yet. And that's going to come down to this formula from up here. F equals ILB. And they need to be perpendicular. Okay, so this wire is going to feel a force that depends on the current flowing through it, which is 3 amps. It depends on the length of the wire. Now, L, remember, is the length of the wire that's in the magnetic field. So parts of the wire that are not in the magnetic field don't count. It's just the charges, just the parts of the wire that are actually in the magnetic field that will feel a force. That kind of makes sense. A magnetic field can't exert a force on you if you're not in that magnetic field. So for L here, we're just going to use the length of the wire that's in the magnetic field. So this 0.3. That's important. And the strength of that magnetic field is 0.5. So if I multiply those together, I get 0.45 newtons. So this wire in green, when it's got that current flowing through it in this magnetic field, will feel a force of 0.45 newtons. That's the magnitude part. What about the direction of that force? Well, that's where our second right-hand rule comes in. This wire is being affected by this magnetic field. It's feeling a force from it. So we're going to use our second right-hand rule. Take your right hand. Put your pointer finger in the direction of the magnetic field. That's the dot, so that's coming out of the page. Your finger's coming out of the page. Now your thumb goes in the direction of the current. That'll be to the right of the page. So finger's coming out of the page, thumb is going to the right. And then your middle finger points perpendicular to both of those, coming out of your palm. It should be pointing down towards the bottom of the page. So that is the direction of the force. And so that 0.45 we figured out from the formula, and this part is from the second right-hand rule. So the key ideas in this lesson are that when I have moving electric charge, like a current in a wire, it both creates a magnetic field, which we studied previously, and it's affected by other magnetic fields, which is what we were focusing on in this lesson. The first right-hand rule tells us about how it creates a magnetic field, and the second right-hand rule, which we discuss here, tells us about how current is affected by magnetic fields, by feeling a force. While the right-hand rule will tell us the direction of that force, there's a formula, F equals ILB, that will tell us the magnitude of that force. And both the formula points out that things being perpendicular is pretty important here. And that's baked into this right-hand rule as well. Right? My finger and my thumb and my other finger all had to be perpendicular to each other. So perpendicularity is important in this concept. Then we did a few examples just to kind of demonstrate how this right-hand rule works, some scenarios where this concept might be applicable, and then just to practice using the formula.